go over what we had talked yesterday, and then I will move over to a description of the various subsystems used in robotics. We had seen yesterday that robots are used in industrial applications, typically to handle, repetitive and hazardous tasks, like in forging shops, in welding shops, and elsewhere in assembly. The other applications of robots are in exploring, inspection, and maintenance in remote and hazardous areas, including the outer planets, the deep sea. So we had run through all these things yesterday, and today I will continue and talk about the technologies and the subsystems used in robotics. Now, the technologies used range from age-old technologies like the rope and pulley to very modern ones. Okay, as more applications come up and as more technologies develop, we will see newer and newer technologies being incorporated into robotics in the future. The trend in robotics is towards miniaturization. You want to build robots the size of little ants. You want to build robots the size of little cockroaches. And that is the trend that is going on, particularly when you are handling hazardous material and all that. You are looking for very tiny robots also. That's the trend that's going on. Energy efficiency is another issue, because if you want a robot to be autonomous, it should carry its own power pack, so it should be energy efficient. You can't afford to draw a lot of power. That's another thing that's being looked into in a very big way. And of course, people are trying to give more and more intelligence to robots, trying to see that they have become more and more intelligent and consequently more and more autonomous. Now, what are the systems that go into a robot in order to help it do all these tasks? We shall have a look at those things. The subsystems, as you can see on the screen, are several. Actuators and transmission systems. Essentially, a robot moves around, so you need actuators. Actuators is a general word to denote several things like solenoids, motors, pneumatic systems, and so on. Then mechanisms, the motors typically rotate, and you would like your leg or your hand to move in a different fashion. You have to convert the rotary motion into a useful motion for various devices. Then you have the power supplies. Motors are driven by special power supplies, power amplifiers, that is what they are called. And we have to address these, because many a time these power supplies are on board the robot. They are mounted on the robot itself. Then power storage systems. If you want a robot to be autonomous, you need batteries and so many cells and so many things. We will have a look at those. Sensors. As I told you yesterday, in order to be autonomous, a robot should know its environment. So sensors are essential. Then of course there is the brain of the robot, the microprocessors and the various other computers, microcontrollers, which control the whole system, all these. There are also the algorithms. All these are there, but then none of these will work unless you develop appropriate algorithms. We will have a look at all these things in a very... Let us see, first look at the actuators. Okay? The conventional actuators are pneumatics and hydraulics. These have been around for a long time. Of course, you have also electric motors. Here is a pneumatic actuator. Okay? It's a simple cylinder with a piston moving, and the piston rod can come out and go in, as you can see. Okay? You can see the piston rod coming in and going out. Can you show the camera here onto this? Oh, yeah, it is there. You can see the piston rod coming in and going out. Air is admitted through this particular port, and it pushes the piston out, it comes out. And when air is admitted to this port at this end, you can see the piston retracts. Okay. Now, when you use this in a robot, you should know whether the piston has gone out. So, a limit switch is used. This is a typical limit switch. This is the limit switch. Now, when the piston end hits this switch, you can see a plunger here. This plunger is depressed and the electric contact is completed, and that is communicated to the controller. So when the plunger is depressed, it means the piston has reached the end of its course. Okay, these two go together in a robot. You have what are known as micro switches available, which are similar to these limit switches, but much tinier. A pneumatic device, once you admit air, let's say it is here, the piston is here, once you admit air, it shoots to the other end. It goes with a solid jerk to the other end. And when you admit here, it goes back to the other end. These pneumatic actuators typically cannot be stopped in between. You can't stop it here. You are either here or you are either here. If you want to change the stroke, what you do is you put a ring out here. So when you come back, when the ring hits the front face, it stops. That's the only thing you can do with these pneumatic actuators. Lately, people have been trying to control and see whether they can attain intermediate position. This is because air is compressed. Pneumatic cylinders are not stiff. Supposing, I put a weight on this, though I admit air, I put a weight on top, then because of the compressibility of the air, this will go down slightly because they are not stiff. Because of the compressibility. A hydraulic cylinder is similar, except that instead of air, I pump in oil. I pump oil. I pump oil through a valve, typically something like this. Oil comes in, goes out into the cylinder. The cylinder will be more or less the same. Okay? Now I can control, in the case of hydraulic cylinder, the motion of this. When I shut the valve, it will stop where it is. And if there is a load and there is oil below, oil is incompressible. It won't move, unlike in pneumatic. Okay? So that is the advantage of what you call the hydraulic system. You could use oil, you have special oils, sometimes even water can be used. Okay? Any liquid can be used, and liquids are incompressible. You can, by controlling the valve, opening and closing it, you can put a motor on top, control this with a computer, open and close and control the velocity. The rate at which the oil flows, if you can control the velocity at which this comes out. You can stop it anywhere. That is the advantage with the hydraulic actuator. But there are problems. Oil, if it leaks, is a potential fire hazard. With the new, no, there is no way. You have to pulse. What they are trying to do is, once the gas starts, the high pressure air starts expanding and pushes it. Even if you shut it down, it just occupies the volume there. So you don't have any control. You have to pulse it. So hydraulics has its advantages, stiffness, and pneumatics have their own advantages or disadvantages also. One of the disadvantages of pneumatics and hydraulics is energy exchange. An electric motor drives a compressor, so there is a loss of energy there. Then the compressor compresses the air, there is some more loss of energy. The air is again in turn expanded in the cylinder to push, there is a loss of energy, there is a friction. So you are paying a lot just for that movement. In the case of hydraulics, you need a huge power pack. Hydraulic power pack where the oil is, pumped through the valves and all. You have to generate the pressure and pump the oil through oil. Okay. Now the oil must be very clean. Particularly if you want to have a very fine control on the valve. If the oil is containing dirt particles, it will choke up and you may not get what you want. You may not get the motion you desire. Oil has to be clean, so oil has to be filtered carefully. There should be no air entrapped in the oil. Otherwise, you are pumping in air and oil mixture and the motion will not be what you desire. The amount quantity of oil will not come in and the motion will not be what you desire. So these are the pros and cons of these pneumatic and hydraulic cylinders. And because of their energy efficiency, today the trend is more towards electrical devices. You can be controlled easily. Okay, direct motors rather than pneumatics. Very heavy systems which have to carry large weight, like use hydraulics. Tiny part handling and even medium sized part handling is done through pneumatics. It's also there because in most shop floors there is an air supply at about 6 atmospheres that is used by the pneumatic robots. Okay. So there they use all these things. Then the most popular form of driving these robots or the actuation of these robots, various joint movements. You have a motor here to move the elbow joint, is what is known as the servo motor. I will show you a couple of servo motors here. I have a very little small servo motors I have brought just for demonstration. Here is a servo motor. You can see the motor is this portion, and this is the gearbox. Typically these run at a fairly high RPM, the order of about 2000 to 3000 or even more. DC, many are DC. There are now of course AC servos coming up, and you can see the gearbox. It's a coaxial gearbox. This will give very little torque. This is only meant for small, maybe about a couple of kilograms centimeters. Inside is a planetary gear. I will show you some of those gearboxes. This can give. See, the one thing you have to remember. I mean, since you have asked the question, many a time, if you look at the torque output of the motor multiplied by the gear reduction, you get a fairly high torque as it seems. But the shaft will decide, the shaft size many a time, or the gearbox may not be able to handle that much torque. In the tiny ones in particular, the small ones. Now this particular one, if I am right, is about 1 kilogram meter torque, not centimeter, 1 kilogram meter torque. Okay. Now there is one more here. You can see this, another servo motor. This has a motor and a gearbox built into this. This is the one we use on the walking machine, and claims that it can deliver about 2 kilogram meters of torque. This one. Now we haven't run it at that particular. One has to see whether it can withstand that, because the gearbox may be, the motor may be, if you multiply it by the reduction ratio, you might get it, but the gearbox might not be. So that's what it is about. So let's go back to the. Here is one gearbox. It's a conventional gearbox fitted onto a motor. No, it's not a coaxial. Many a time, if you want coaxial input and output, the motor shaft is in line, the gearbox output is coaxial. Then you use what are known as planetary gearboxes, as somebody had mentioned, or you could use what are known as harmonic drives. It is important that the weight of the gearbox be as low as possible when you use in robotics. You don't want to lift gearboxes, you want to lift a payload. As I told you yesterday, the shoulder lifts the elbow motor as well as the wrist motor. So unless these motors are tiny, or you position all the motors at the base, you will have to have very light gearboxes. Harmonic drives promise you very light, they are very light harmonic drives. So we will see the harmonic drives at a later date. Okay. So that is as far as this. Mostly we use what are known as permanent magnet motors. In the past, the permanent magnets were not very powerful. Don't get much torque from them. Today, we use what are known as rare earth magnets, and they deliver powerful magnetic fields. They have a very powerful magnetic field. Consequently, for a given size with a rare earth magnet, you get more torque than the conventional magnet. We don't use electromagnets in the field coils because they will absorb energy. Okay, so that's the problem with the electromagnet. It will absorb some amount of energy. The permanent magnet. A very popular motor which most of you are very familiar with is the so-called stepper motor. Most of you are, many students who take up robotics in the first instance like the stepper motor. You give a train of pulses, it goes through some 1.8 or 0.9 degrees. There is an electronic feature. There is one stepper motor used in a disk drive. You have taken it out of a disk drive. The moment you give it a series of pulses, it will go through 0.9 degrees or 1.8 degrees, depending on how you have configured the electronics. They are typical. Okay. So now you can tell the motor go through say 20 steps, 20 into 1.8, 36 degrees. You send as many pulses and it will go through that and stop. The problem with these motors is they are very sensitive to load. You have to very carefully design them. Varying loads, if you have to very carefully, the stepper motors in particular. You have to design them, you have to match the load with the motor very carefully, for the case of the stepper motor. The servo motor, as the name implies, what it does is it obeys a command and can rotate to the requisite angle. A command given by you, rotate through 90 degrees, it obeys. The electronics and the controllers make sure it rotates through 90 degrees. Obviously, somebody has to tell you whether it has rotated through 90 degrees. So what we have is, most of you must have studied in the automatic control course, a feedback. So somebody has to sense the angle, some device has to sense the angle through which the output has rotated and communicate that to the controller. Those are typically done by what are known as encoders. We will see this later when we come to it. This is the, so here is one example of a servo, there is another example of a servo, and is also. Now these days the motor electronics, control electronics are mounted on the motor itself, even for big servo motors. So let us look at it again. The servo motor essentially consists of a motor, a gearbox, the electronics mounted on the back of the motor in order to accept computer commands. Then there is a feedback element. We will see what that feedback element is there, which feeds back the position of the output or the position of the input, whichever it is, depending on how you have configured your motor, to the controller. Okay? And then depending on the voltage or the current through the motor are adjusted by the controller in order to get the requisite motion. They use permanent magnets because they give you a lot of punch, reduce the weight. So these have become the most popular things. Typically DC motors were used for a long time as servo motors. So you had those brushes commutating. That was a source of sparking and noise and wear and tear. Now they have come out with what are known as brushless servos, where that is eliminated, that problem is eliminated. Now they have also come out with AC servos. As you go through the course, you will see a little more details of all these particular devices. For the moment, we accept that a servo motor is one which on command will rotate the output to a specified amount, with a specified velocity. Now let us go to the more high-tech. Today, as I had told you, we have polymers which, when subjected to an electric field, you keep a piece of polymer like this, subjected to an electric field through two plates, capacitors, it will deform. Use this for actuation. You have shape memory alloys, essentially those you just virtually squeeze into, you have an antenna in space, you want to send it up, the spacecraft up, you would like to fold the antenna, keep it inside, and then when the spacecraft has reached orbit, you open up the antenna. So what you could do is make it out of shape memory alloys, virtually crumple the antenna, reheat it and bring it back to shape. They retain their shape, they memorize their shape. Then there are piezo patches, these are available in our robotics laboratory. They simply look like a bit of sticker which you use, maybe about an inch square, typical sizes. Now let us say you have a dish. On the dish you put the piezo patch, pass an electric current, the dish will deform out there like this. The piezo patch has an advantage. If you put a force on it, it will give out a signal. So you can use it as an actuator as well as a sensor. Now one typical application of the piezo patch has been, there is a dish antenna on space, and let us say the antenna is sending a beam towards Mumbai, and you want to deflect that beam towards Calcutta, the other end of the country. Now one way is to turn the whole antenna or the spaceship or spacecraft and point it again towards Calcutta. Another way is slightly deform the antenna to shift the beam by a few degrees. 1 or 2 degrees in space will translate into several miles on ground. So piezo patches are being used as actuators in we saw these piezo patches being used as actuators in tiny devices used for electronic assembly and solder. These piezo patches are being used. Now all these actuators require specialized power supplies called one of them is the pulse width modulation amplifier. If I want to control the velocity of this particular motor, one way is to change the voltage. The way we do it is, in this DC motor, is to change the voltage across it. How do I change the voltage? You are all familiar with the potentiometer. Put a DC on one side, you can changing the intermediate position of the rider, you can get a output which is different. Say if you have a 10 volt input, you can get 5 volts, 2 volts, 3 volts. So you keep on changing the potentiometer, move it up and down, the speed will change. But then remember, this is a resistance based device, the whole thing heats up, you are losing energy there. So they came out with PWM amplifiers. What they essentially do is nothing, they switch the DC at very high frequency. If you pass it for a certain amount of time, you will get 10 volts. If you pass it for a lesser amount of time, for a given cycle, you will get 5 volts. So you can control the voltage and accordingly speed. There is no loss due to heating. There is, of course, otherwise in electronics, but the loss is not as much as when you use it. These are the various things which are being used. So these are the various actuators which are being used. Mostly you find the conventional actuators being used very heavily, but the trend is towards using these high-tech actuators. The linear motor, I shouldn't call it, I should have put it probably in the conventional. Nothing, take a motor, conventional motor, cut it and unwrap it. Cut it, unwrap the motor. So you have all the coils of the armature spread out. You keep the magnets and then the solenoid, or reverse. Instead of rotating, you unwrap it. That's a linear motor. For a long time, the linear motors could not provide the requisite punch, but now they have come out with, with so many special magnets coming out and so many other material coming out. You have got linear motors which are now equipping machine tools. So you have in a machine tool for the carriage motion, you have a motor, you have a screw, and you have a nut, and then the whole carriage moves up and down. Then from the motor there is a gearbox to the screw and all that. You can eliminate all this using a linear motor. Simply a stator and a rotor all spread out and it moves. So they have become very popular. Okay. So let's now go on to the next one. Here I am showing you what is known as a pancake motor. You can see the motor driving a special robot, high-speed robot mechanism built in the robotics laboratory here. And you can see on the top there is a motor. That's a very thin motor. The black box on top is the tachometer. A tachometer essentially senses the velocity. Below that there is the motor. The tachometer is standing on 3 pillars. That's why you see the gap between the tachometer and the motor. The motor is below. It's a pancake motor. It's a very thin motor. The rotor is something like a PCB. I won't go into further details. It's just like something like a PCB. It's very light, so that the motor can accelerate very fast. See, one of the important requirements in robotics is the ability to accelerate very fast. So we have used the pancake motor in this particular experiment. He was trying to build a high-speed robot. You can see the electronics beside it. Here is the same. I had shown you this particular servo motor, the same used in the walking machine. They range from very small sizes. Now this is one of our old ideas which some student of ours had come out with. The stepper motor is conventionally a cylindrical motor right now. You have the cylindrical motor. There is a cylindrical rotor and a cylindrical stator. Why not a spherical? It's a ball and socket. You have these magnetic coils in small grids, and then you can move it in whichever way you like. Otherwise, you will need several motors in order to get this motion. Now, people have been attempting now to build this. There are problems, but lubrication, keeping the two together, all sorts of engineering problems are there, but this is what people are thinking of. Then you eliminate 3 motors, because when you have a ball and socket joint, you can have several motions, including a rotation of the ball around a particular axis. So all that is possible. So people are thinking of this. Now these fancy actuators like high-tech actuators like all these polymers and all are being used to propel things like the fish, and a submarine is usually propelled by a propeller which spins, whereas a fish, it moves its tail, it moves its fins, and then it moves. Supposing I distribute the actuators all over the surface through patches, make the skin, make the body deform, make the body move the way I want, I could perhaps get there. That's what people are attempting to do. Here is the internal structure of this particular fish. Then once you have got the actuator, you have to convey the motion to the point where you require the motion. That's what you have to do. So you use gears. These are well known. I mean, I don't have to go over them because you all know about gears, gearboxes. Lighter the gear, the better, because the gearbox has its own inertia when you want to accelerate. You need mostly a positive drive, but of course, so that's quite important. Chains are used, plastic chains, non-metallic chains, I should say more clearly. Timing belts are quite important. You see? Then metal belts, ordinary belts you have seen the metal belt. You must have seen it. If you go to the carpentry shop, when you go to the carpentry shop, in woodworking machine, you have the band saw, which is nothing but a metal belt. So that technology is being used. The advantage with a belt over a timing belt or a gear is, for example, in your tape recorders, you will never find a gearbox inside. You will always find belt drives, because otherwise the small velocity fluctuations can distort the voice that is being recorded or played back. So metal belts, cables and pulleys, pulleys and cables, that's like the rope and pulley technology, they are also being used these days by most people. For example, there is a robot which can play table tennis, where the entire drive is through cables and pulleys. It's called the VAM. Timing belts we have used in our walking machine also. But when I want smooth dynamics, I would go for the cables and pulleys. Which timing belt? So I will show you later. There will be a small. A timing belt is nothing but a conventional belt with the teeth on the inner side. I should have brought one and showed the teeth on the. It engages a gear-like pulley, which also has some. That's the timing. Then you have linkages. The ball screw is a very important component in robotics, particularly the industrial types of robots. Any one of you who has seen the numerically controlled machine, in a lathe for example, the carriage motion is through a screw driving a nut, right? The carriage motion. Now if you want precision and low friction, between the nut and the screw, the balls are kept. So it eliminates friction, like a ball bearing. And you can preload the whole thing so that you eliminate that backlash and all these problems. So ball screw is a very important component. And many a time, you see, in a robot, just imagine your own hand. Most of the time you can understand industrial robots and many robots by looking at your own human body. You can't move the shoulder at a very high speed when you are repetitively doing a task, or the elbow at a very high speed. But motors typically move at high speeds. So you have to convert that motor's high speed to the low speed you require. One way to do that is drive a screw, move the nut here for example. The nut is here. So when I drive the screw, motor is, as I move the screw, I am holding on to the nut. Otherwise, let me spin the nut, you will see that nut comes. See, this is. Okay. So what I do is I drive this nut. The nut is now like a piston moving up and down as I move that. So I have a connecting rod like the engine mechanism, and the crank will oscillate depending. You can now use the inversions of the slider. That's a slider crank. What I have done is I have used the slider crank. but I get a large speed reduction because of the presence of the nut and then I convert it. This is used. Or you use it in the inverted slider crank mode. You know, you have seen the bulldozer where this pneumatic cylinder is pivoted to the ground and it pushes and opens up. Okay. So instead of this, I put this motor and the nut here. So instead of the piston moving, the nut and drives whatever. So these are being used essentially for. Then you have lots of mechanisms which are used, which convert this motion into useful motion. We will have a look at some of the mechanisms. For example, the leg of the walking machine we had built in robotics lab, Natraj, is a what is known as a pantograph mechanism with two inverted slider cranks driving it. If I go into the correct terminology which I use, the inverted slider cranks, as you can see from the, you have the green and the reddish colored servo motor. On top of it is a black colored gearbox. On top you can see the pulley and the timing belt. The timing belt drives a nut up and down, which in turn moves the lever at the bottom and the leg lifts up or down. Like this, this is what we have done. Now we have used the ball screw there. Ball screws have limited life depending on the load, just like a ball bearing has limited life depending on the load and speed of operation. So maybe once in few years we have to replace those ball screws. So that's the way the design has been made. So this is a mechanism which converts the rotary motion of the servo motor into the useful motion of my leg. Here we have used chain drives. You can see the stepper motor. There is a stepper motor driving the base rotation like this. There is another stepper motor mounted here which is driving the elbow joint. The stepper motor from a chain drive driving this particular, providing. You can see the stepper motor here. See the stepper motor. Correct? You got it. So all sorts of transmissions and mechanisms are used. Here is a cockroach running on a treadmill, pneumatically actuated. There are small, tiny. You know, you get this. You can many hobbies use these syringes to make these pneumatic piston and cylinder. So many persons. You can see the cables, not the cables, say pneumatic. This is built at Stanford University. Okay, conveying the pneumatics, and you can see the cockroach. There are three legs which you can see. They look like pencils with erasers. Three legs. It's not pencils with erasers, but they look like pencils with erasers. It's a cockroach, and it's moving on a treadmill. Okay, they have used pneumatics and they have used a peculiar mechanism. So mechanisms are important when you want to get the desired motion you want. Okay. Similarly, for eels which can swim in water, this is the mechanism. And you can see the eel swimming in water. Okay, artificial eel, all power, everything is inside. So these are the various mechanisms. And, so you see the area is vast. It starts with electronics and. Now we also have power generation and storage systems. I had told you about it. Solar cells generate power. If you want to work in on the moon or on Mars or in space, solar cells are used generating power. Yeah, if you have a very large robot, you can put a solid power pack like a diesel engine on top perhaps. But in the tinier ones, you have to find some way of keeping. Fuel cells, you know, where hydrogen and oxygen combine to give you electricity, and these are also used. Then rechargeable cells. Rechargeable cell technology. We have the conventional batteries, lead acid cells. They are very heavy. Natraj uses the lead acid cells, which are very heavy. You know, we had no choice, but we are not getting any. We were not getting any. Half an hour it can run on rechargeable cells, a walking machine. But today, technology has gone so far ahead in mobile phones and so many gadgets. You have these rechargeable cells which can store a lot of energy for a given weight. You know, there's a lot of innovation in this direction. Recently, if you recall, they had sent an aircraft which was supposed to stay out there for about a month or so without needing any refueling and all. What it was essentially doing was picking up solar energy through solar cells And for nighttime operation, or when the sun is not there operation, this energy was being stored in fuel cells. It decomposes water. So when solar energy, electricity is generated by the solar cells, that is used to decompose water, which are stored as hydrogen and oxygen. And when you need power at some other time, and the solar cells are in the dark, you recombine in a fuel cell oxygen. See, the amount of imagination that is exercised in the design of modern technology, something which we should not forget. The limit is, there is no limit, endless. So this is what they use in motion. We shall now look at what are known as sensors. Very simple switches like this limit switch which I had shown you. This could be used as a sensor. Yesterday you had seen that movie of the rhino robot picking up a glass, and transferring the contents. What you did not see, what was not visible, was below the glass, that stem glass which was there is a tiny switch. Okay, unless the switch is closed, the rhino's program would not have started. So unless you put the glass, the rhino's program will not start. See, we were using it for an exhibition. We wanted to make sure people don't start the robot unless the glass is in position with the contents. So a limit switch is a sensor. Many a time a robot is blind. It has no sensor. Conventional robot. So it has to pick up an object. It will go up to that and close on to the object like this. But if the object is not present, it won't know. It will simply go through the rest of the motion. It's pointless. So what do? You put a small switch here and it closes, like the refrigerator door switch. Simple. There's a very simple. So a lot of things can be done with these. Otherwise, a force sensor. Natraj, for example, the walking machine, when it puts its foot down, we'd like to know whether the foot is down. And what is the distribution of weight on the 3 feet on which it is standing? It has 6 feet. It uses 3 feet to stand on and throws the other 3 feet forward. We would like to know all that. So we put a force sensor. Or you would like to know how much is the gripping force when you are holding a particular object, because it's a fragile object, it's a glass, made of glass. So you would like to know and say that beyond that grip, don't move the fingers. Once you have reached a particular force, don't move the fingers anymore and grip it harder and break it perhaps. So we use what are known as force sensors. Force sensors are numerous. There are a number of force sensors which are currently available. And the technologies and gyroscopes, which will tell you whether the walking machine or the mobile platform is horizontal, or is it climbing up, or is it tilted down to one side. These are being used here. The very tiny gyroscopic chips are available now. Very tiny, very small. Previously there were gyroscopes for rotating masses, large ones. Now all in the chip. They are used in cars, number of them, for various purposes, to sense various purposes. A car today has several sensors, plenty of sensors in it. Potentiometers. Here is a rotary potentiometer. I would like to know how much my particular motor has rotated. I connect it to this potentiometer. When turns, it's an absolute way of measuring. See, at one end it will be 0 volts, at the other end let's say it is 10 volts, full output. So if you go halfway through, it will be 5 volts, provided the potentiometer is a linear one. That is, the displacement versus voltage should be a straight line. If you draw it, it should be a straight line. So I can directly say how much degrees I have gone through. I can calibrate it and say. Then encoders. Encoder is slightly different. I have got one encoder here. It's going to be pretty tough for you to see what is inside. You can see this. Okay? You can see in the monitor, perhaps you will be able to see. You can see the encoder, electronics. What is this encoder? Essentially a rotating disc which is mounted on the shaft. Say something like this. I have got this here, something like this. A rotating disc mounted on the shaft. Now you have got a lot of lines scribed out here. You send a light beam and you have a light receiver here. The beam must be very thin. As each of these lines cuts the beam, a signal is generated on the other side when the light is restored. So you have a measure of how much you have rotated.
But look at the size.   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 But look at the size. But look at the size.  But look at the size.  But look at the size. But look at the size. But look at the size.  But look at the size. But look at the size. But look at the size. But look at the size. But look at the size. But look at the size. But look at the size
the disc inside, which I cannot pull out, has about 2500 lines on its periphery, radial lines. So how thin must the light be, and how thin corresponding to the receiver, everything. And the electronics is here. So this is the one that gives you the position of the shaft as you rotate. These are known as encoders. These are incremental devices as against this, which is an absolute measuring device. It tells you how much you have gone through from the previous position. This is an absolute measuring device. Tachometers, these are essential. These are known as internal sensors, the potentiometers, encoders and tachometers, particularly because they are used with these actuators. A tachometer, I have got one here, essentially a generator. Depending on the velocity of the shaft, omega, angular velocity of the shaft, okay, you get a voltage out. Again, if you plot angular velocity versus voltage, it should be linear. You can use it. You can measure the speed at which the shaft. You can instantaneous omega also can be measured by a tachometer. It's a fairly large tachometer. See, when you want to control a motor, you would like to know how much position it has gone, whether it is accelerating, decelerating, then you can do it much better control. You would like to know the velocity. Just by looking at the position, you say, let's say, you have given a command, go through 90 degrees to the motor. It started rotating. It would like to know whether the controller would be much more effective if it also knows what is the velocity at which it is rotating. Because, it has to start from zero velocity, pick up velocity and bring it down. Pick up speed and then bring it down. So a tachometer is used. Sometimes the tachometer information is obtained from the encoder itself. But sometimes this is a fairly rugged tachometer used in industry. Yeah, like a motor and a generator, DC. We have to make sure it is linear. Speed versus voltage, that's important. Many a time, this is a encoder used in some of the tinier, smaller units, but there are rugged encoders which are larger than just heavy duty encoders. So they come in a variety. I have just shown you a few of these. Then you have the cameras, vision systems, the proximity sensors. Something comes near infrared, light is bounced off, and then and the list is endless. It's all your imagination that limits you to. Now, the potentiometer, for example, gives an analog signal. Okay, this has to be converted into a digital signal because most of the controllers today are digital electronics. In the past, they used to be analog. Because the digital electronics give you the requisite. So, you have to convert this signal. 5 volts equal to this particular 8-bit word. 10 volts equal to another particular 8-bit word. Like that. You have to convert. So, there are what are known as analog to digital, which will talk with this. Reverse is also true. Sometimes the controller gives out a digital signal, and that may have to be converted into an analog one to drive some system. So, these are all there. Then there are microcontrollers, very small, the whole computer in a small thing. There are power electronics. I told you about the PWM amplifier. The whole thing comes in a small chip of this size. And then many of these MOSFETs, and these are all required in order to drive your motor. This is the various. You can see what we had built for Natraj, the walking machine built at, these are the servo motors, and you can see the various electronic boards which are out there. These were built in the laboratory by our students and engineers, tested. Of course, last but not least, in order to put all these together and make it work, one has to think, right? That's where the algorithms and software come in. They occupy a very special position, as important or maybe sometimes even more important. You can't have a machine sitting there if it doesn't know what it has to do and how it has to do it. All that is through the software, all that is imparted to it. The control of motors and actuators, now there are various equations to be written, there are various, you get You want the motor to rotate through a particular angle, you get information from the encoder, from the tacho, how to put all this together and control it so that it goes and stops where you want it. Control algorithms are required based on. Now planning the trajectory of individual actuator motions. Do you want it to accelerate? Do you want a straight line? Do you want uniform velocity? Once it accelerates, attains a uniform velocity, comes down. Or do you want the velocity to move along some polynomial, some curve of the motor? I'm talking of motor shaft as it goes through those 90 or 100 degrees. All this has to be planned by somebody. But today, of course, most of them, as I showed you, many of these systems sit on the back of the motor. You just tell the motor go through 90 degrees, this fellow takes over. So everything is distributed, electronics. Okay, you communicate your command to the motor, and the motor, the chip on the motor, the controller chip on the motor, that takes care of all these calculations. You have to look at the load, the disturbances, how to compensate for them. All these things are done by that. Now, when you want the robot, say an industrial robot holding a welding gun to move along a trajectory, somebody has to plan that trajectory. You will typically give some points on the trajectory, and somebody has to plan. Somebody has to plan the velocity along the trajectory. If you are welding along a curve, you should move at a uniform velocity along the curve. Somebody has to plan. Somebody has to calculate what should be the individual motor motions in order to get that. Okay, so all these are there. Planning trajectory of individual actuator motions from the trajectory of end effectors. We have the so-called kinematics of robots. Or you have a motorized vehicle behaving autonomously. It has to reach a particular spot. It has to avoid some obstacle. Who plans it? The wheeled vehicle. What is the path it should take? Well, okay, you have got the path. What are the velocities it should maintain? Okay. What are the individual velocities of the individual wheels in case all the four wheels are independently driven? All these are done by the software. So there is a lot. Okay. Accepting and acting upon sensor inputs. There is a rock in front. As my robot moves, mobile robot, what should it do? How should it avoid? How far, how much of a gap should it? All these are. Sensors will tell it where the rock is, how far the rock is. The vision sensor or just a simple proximity sensor. In a shop floor environment, you might get away with a proximity sensor because everything there is known. You know where things are. Unless, of course, the unexpected happens, most of the time you know. Or a horse walking along. It has to choose its footholds. Where shall I put my feet? At the same time, at any instant, am I on 2 feet or 3 feet, or am I on all 4 feet or 1 foot? It may just topple over if it is on, if you have not controlled all these things. So all these controllers are done, controlling is done. Look at the, in nature, of course, it's far more sophisticated. When you look at a movie of a lion or a tiger running, you see the way the body contour, the whole thing goes, the whole body. It's not just the feet running. The head moves, the tail moves, the body flexes. All this is done. That means there are a lot of actuators all over the place which control, and simultaneously it watches, it senses, it feels with itself. And we all do that. So all these tasks have to be planned by somebody, and that is where the controller, the computer controller comes in and looks after all these particular things. So with this I conclude this lecture just by summarizing that today we have seen the various subsystems used in robots. We have gone from the component level more or less to a broad level. From the next lecture onwards we will be going into industrial robots, which we will use as a vehicle for, as a means to tell you about robotics to a great extent, and later on we will touch upon some of these mobile robots, walking machines and other robots. Thank you.